and roll. Okay, people, any questions that you have regarding the advanced circuitry, Gauss law, or you're totally struck by the electric field? You said, "Piang," died. How was the Gauss law and the advanced electric field, the integration? Okay, the look of helplessness. The look of helplessness. No worries, there'll be more coming today. In another form. Okay, we'll start off easy first. We'll start with the IB first. Then we'll go advanced. Then we'll go really advanced. Then we'll go relativistic. Yeah. Then we'll go relativistic, which means really fast. Okay, so let's start off with some fundamentals that you feel very comfortable and very, very intellectual with. EM, one of my personal favorite. Why? Because it marries two different areas together. You're talking about electricity and you're talking about magnetic field. So in the past, it was seen as two separate forces, two separate effects. But it was Maxwell who came out and said, hey, they are not two separate effects, they're actually one effect. It's electromagnetism. Almost like Albert Einstein who shook the world when he said, it's not space, it's not time, it's space-time. Yeah, it's space-time. It's not like this and this, it's like this. One mass like called space-time. So like EM, it's not electricity, magnetism, it's one thing. Okay, one of the things that scientists have yet to be able to mesh is EM with gravitational field. In fact, gravitational field is the loner which refuses to merge with other fields. Scientists have been able to come up with theories that can merge nuclear strong force, nuclear weak force, EM force, but gravitational force stays elusive. So probably one day, one of you. Well, okay, so electromagnetism, the simplest part of it, the simple part of it is this and this. This is how electricity creates magnetic field and how magnetic field interacts with, who's that? Who's that? It's weird, right? Open the door, laugh, and then run away. It's like stalkers. Which one of you gonna stop? Oh well, too bad. Wait, you just have to bear with this. Okay, EM, magnetic field interacts with electricity. So we begin with the left side. You definitely will know this. Don't prove me wrong. So you got I over here. Inside your mind, imagine the direct. I can see your right hand coming out already. The right hand is the right hand. Okay. So I allow you to imagine for 3 seconds how the field pattern looks like. Okay. 1, 2, 3. Okay. Now check whether the field in your mind is the same as the field that I've drawn. Now there are 3 things I look out for in this diagram. 3 things. You may think that it's just a diagram. 3 things I look out for. First thing, the shape, which is circular. Second, I'll look out for the direction. Now right hand grip rule. The thumb represents the current, correct. And then the fingers represents the field. Now think about this, KIV this, but I won't give you the answer. Think about this. Why the right hand grip rule works. Think about KIV this, think about it. Why does it work? Fleming's left hand rule. Why does it work? Think about this. There is mathematical basis, but I shall not introduce you to that right now. Just hold that first. Think about this. Separation is a little bit easier. The separation of the field lines gets further and further away. Why? Because the field gets weaker and weaker. So the third thing I'll look out for is separation. Now this is the language of fields. Whether it's G field, E field, B field, it's the same. When the field gets further and further away, the strength gets lower and lower. So it's almost like say when you draw this, people know that it's love. Right? This is universal language. So when you draw a field strength like this, which side has a stronger field, A or B? Exactly. So it's like almost like language kind of thing. Yeah? Define language. Now, for a coil, that's the next thing you need to know. For a coil, this one, some people with spatial issues, cannot see means some people cannot see means cannot see. How to turn? They somehow can see, like, you know those kind of diagrams with negative space kind of thing. Some people just cannot see means cannot see. You know, when I first saw Batman's logo, I know, like this, and then it has this, and then it has this, and then something like this. Yeah. When I first saw it, I was like, what's this horror movie? Got 3 teeth on the bottom and then three tooth at the bottom and then 2 tooth at the top. I was like, I can't figure out like what's this? I kept looking at this portion because there's 2 teeth, 2 tooth over here and 3. I couldn't see the Batman, okay? It took me a few weeks, oh, it's Batman. So I just cannot see it. So some people have issues. And okay, let's see whether you have that or not. Okay, the dotted lines means that the lines are behind. Solid line means that it is in front. Some of you look puzzled already. So, very simple one. Let me teach you. Let me show you. You only need to look at the current on the top and at the bottom. Only need to look at the top and bottom. Don't be confused by the whole setup. So in this case, the current goes in at the top, comes out at the bottom. So therefore, you use your right hand grip rule. Now your fingers becomes the current. So it goes in at the top, comes out from the bottom. It goes this way. So it goes like this. Now something you need to be very careful of. And I think IB recently, they're really getting smart and setting good questions. You're smarter. Not smart, smarter. So they're smart already, it's smarter. It's like writing this kind of term comments. The student is improving. The student is improving. When you read the term comments, it must be really read with some alternate interpretation. The student can cope with stress. Means what? Bo chap. The soldier is very vocal. Talkative. Right. So let's take a look at this. So the thing that you have to be very careful about, trick, is that this part and this part, the field points opposite direction to the field over here. Remember this. Remember this, be very, very careful about this. Now this presents a problem, say for example, let me show you how I can apply this in a question and create a trick. So say for example, A and B. The current in the loop is this direction. What's the direction of the field at A and B? Why not we use the chance to test how much of EMI you remember? Just a dipstick test. You know what is EMI? Do you know Mr. Faraday's and Mr. Lenz? Yeah. Okay, good. So let's see. Let's see how much of it you know. I got 2 loops over here, loop A and loop B. Okay? Now this loop over here, the external loop over here, has a current that is increasing. Okay? Your task is to tell me the direction of induced current in loop A and loop B. Give it a thought. Oh, what's that? What? You still okay. This is the loop where the current is flowing and increasing. There is a loop A that is inside, the loop A that's inside the bigger loop, and there's a loop B that is outside. Clear? Okay, can. Now you clear the context, Okay, good. So the question is, what's the direction of induced current? I'll give you 30 seconds, think about this. Let's concentrate on loop A first, otherwise you'll be thinking both at the same time. Let's focus on loop A. So remember Lenz's law? What's the most important word in Lenz's law? It starts with the letter O. Oppose. Yeah, close. Oppose. Yeah, oppose. That's the key word, oppose. Oppose the what? Oppose the... Okay. I'm not asking a bit too much, but by incorporating EMI, but I think let's try use this as an opportunity to revise. Okay. You see, sometimes this kind of question, right? If you guess, 50% chance, right? It's either clockwise or anti-clockwise, right? Some students can tell you it's into the page. What? You just violate the laws of statistics. It's like it's either this or this can tell you into the page. What's the coy? How to into the page? Okay, let's take a look. Let's see. Let me just think through what's the answer first. Okay, how many of you say that it is clockwise? Clockwise. For A, clockwise. Okay, looking around, looking around. Sure not? Sure not? Clockwise is this way, in case you haven't seen a clock before. Anti-clockwise is this way. So clockwise or anti-clockwise? You sure not? So let's check again. How many of you say it's clockwise? Okay. How many of you say it's anti-clockwise? Okay. So the answer is all anti-clockwise for A. Okay, let's check out whether it's correct or not. The field created by this loop over here, really not thinking about the increasing or decreasing, right? What's the direction of field over here? In, out, left, right, up, down? Into the board, correct. So the field is into the board. Okay? Into the board, and the field is increasing or decreasing? Increasing because the current is increasing. Now to oppose that change, that increase in field into the page, the flux or the field created by loop A must be pointing in or out. Exactly, it's pointing out, so it's going anti-clockwise. Yeah, Ken? So all of you correct. But I don't know whether you can get the correct reasoning or not. I hope you can get the correct reasoning. Now take a look at this. What's the direction of field over here? What's the direction of field over here? In or out? Sure not? You use this, it goes like this, it's in or? This one, it goes in and comes out. This is the place where students will get caught. This is the place where students will get caught. Yeah, it's in and it's out, and then it's increasing. So you to oppose the increasing field out of the page, you create a field into the page, so the current will be clockwise. Can be careful. This is how I can incorporate EMI. I mean, I know that I'm bringing something that's in the future a little bit forward, but I think it's a very good question that I really, oh man, when I saw this question, solid. Yeah. Students used it from the loop A, will think in and then in. Then you're in it. For A, okay, for this, you mean the induced current or the current that is outside? From the outside, the current is such a way where the north pole is on the other side. Yes, correct. So then how come the magnetic field is pointing towards the north pole? Oh, the reasoning is that if you have a field over here increasing, it will try to oppose the increasing field by producing a field this way. You'll try to reduce the field that is increasing. Oh, the X is due to this, not due to the induced current. The X over here is due to the current that is flowing on the outer loop. No, if you have a north pole over here and south pole over here, it is inside the magnet. Inside the magnet, the field points from south to north. Oh, but then outside is north. Yes, correct. Oh. Correct. Okay. Ken, have I answered your question? Okay, good. Ken, okay, so this is the, I showed that this is something to be careful of, and then in the context of a question, how can I test whether you know or you're careful about this? Okay, so very simple. Two parts. You need to know the field of a wire, and you need to know the field due to a coil. Now we move on to the second part, which is this portion over here, which is more interesting, meaning more difficult. You're lucky, you don't need to know moments. Surprising, right? Physics, moments not in syllabus. It's like, what? The reason why your table doesn't fall, why you don't fall off the chair is because of moments. Yeah, so it's puzzling why it is not in your syllabus. I would definitely teach it. It is definitely something very important. And because moment can be incorporated easily into this portion. For more questions, more way to torture you all. Okay, let's take a look. So whenever you have magnetic field interacting with electricity, you always have a force. And is force, please don't disappoint me, is force a vector or scalar? Oh no, scalar, that's it. Scalar, you need to go back to Sec 1 already. Okay. But some force probably easier. How about, say, charge? Charge got positive, negative. Scalar. Current is a vector or scalar? Current is a vector or scalar? You got positive current, negative current, right? Current is a scalar, correct. Current is a scalar. Yeah, current. Pressure, is it vector or scalar? It's force over area leh. So vector or scalar? Ah. Pressure is a scalar. Pressure is a scalar. Because pressure, if you apply, it acts in all directions. It's yeah. When you apply to a fluid, it acts in all directions. It's a scalar. Like in one of the other lessons, it's a dot product of force and area. So it results in a scalar. Okay? Moment is a vector or scalar? Remember, clockwise moment, anti-clockwise moment, right? So got direction, right? So it's a vector, right? So how? Then you look at force. For a vector to be a vector, for a quantity to be a vector, you need direction. We should have a continuous variable, right? In terms of direction, I should be able to point anywhere. Right? Force can point anywhere. But moment, only clockwise, anti-clockwise. I'm challenging. Okay, it's not about moments or whatever. It's really about how do you know, how do you define a vector scalar, and how do you know that quantity is a vector scalar? So, okay, the answer is moment is a vector. Is a vector. Okay, you gotta think about this. Why? You gotta find out why. Okay. You got magnitude and you got direction. Okay, you got magnitude and direction. Let's go for the non-mathematical equation first, something that you learned before. Let's build confidence from there. Let's see whether you know how to use your Fleming's left hand rule. You got I, you got B over here. Okay, why? Okay, guess what B represents? Magnetic field. Question about this? Why magnetic? Correct. Why magnetic field B? Why not MF? Why not M? Don't get it. Magnetic field, Ethan, magnetic field, don't get thinking too creatively. Magnetic field. Why not MF? Why not M? Why not F? Why B? All of like MB. Yeah. Wow, that's really that sounds like some variety program. You try to bullshit people through. Okay, the reason why I think I don't know why I didn't read about history, because there's this pioneering work by this person called Bayard. He's a scientist, Bayard. Yeah, Bayard. And that's the reason probably why it was he's a pioneering figure in the field of in the area of magnetic field. So together with this other scientist called Savard, they came up with the BS law. BS law, yeah, the BS law. Yeah, the BS law. Wow, that's nice, man. In my 15 years of teaching, I never saw it as a BS law. No. Okay, if given time, I will show you how to use this law, what this law is and how to use this. But for the moment, I think it's because of this person, that's why it called it B. Now, can you tell me what's the direction of the force? Do you remember no? Left hand rule. Some people got those psychomotor skill one. Cannot like then it become like this. No, it's I'm showing difficulties in showing what nonsense. Some people just got difficulty. So like this, like this. If you got difficulty, like this first. Ping. Okay, can? So father, mother, child. Father, mother, child. Force for father, mother, magnetic field, child current. Okay? Don't attempt to write this on your fingertip, please. Don't get write FMC. And don't get your IB diploma because of this 3-letter. So the thing is, father, mother, child, if you apply this, can you tell me what's the direction of the force? So if you happen to be like Bharat now, almost like spraining your wrist, Because I intentionally make it such that you have to do this and then like this, yeah? Like this. Now, one trick is one is going in. Yes, correct. The force is in. Yes. Wow, newfound ego, man. Newfound self-esteem. Okay, one of the tricks that you can do is to make your life a little bit easier, and your friend will thank you for that, is that you can reverse the direction of one of them. It might make your life a little bit easier. So you reverse, say for example, if you're like this, right? You reverse the direction of current. Then the force is easier, right? Rather than this. So the thing is, it is easier if you point it this way. The current is reversed, but the field stays. So the force is out. Then you just need to reverse the force. Yeah, it might be easier at certain times. But you shouldn't make a tree 720 degrees. That's really idiotic. Like, I'll touch your left ear. Like, some people... If you make a 720 degrees turn, it means something is wrong already. Okay, so usually you don't need to. Very simple. Let's try something else. Let's try something else. How? Improvise Fleming's left-hand rule. Like this. Improvise Fleming's left-hand rule. Not 90 degrees like this. Then how? 怎么办? Okay. One thing I'm going to tell you, it's going to work for all cases. Whenever you deal with magnetic field, always think perpendicular. Always think perpendicular. So which one do you resolve? Which one is a vector? Current or field? I thought we had a discussion just now. Current is a vector or scalar? Scalar, right? So cannot resolve what? So when people tell you resolve current means wrong. Cannot resolve current. You can only resolve field. So some people also got problem. Resolving field, they can never comprehend how you can resolve it this way. Some people cannot. Like say for example, we learned this one, right? Some people, you tell them to draw 200 times, they'll tell you the resolving this one goes like this. Some people cannot see that it can be resolved this way. It may be simple to you, but some people just cannot visualize why this is wrong and this is correct. So the way to resolve this is always to resolve parallel and perpendicular. So we call this B perpendicular, B parallel. Yeah, if we add in this feature, this angle over here, this is theta, this will be equals to B sine theta, this will be equals to B cos theta. Now you use your left hand rule and tell me what's the direction of the force. Which one? Which either way? Whether you choose to resolve current or resolve. Correct. You still get it, but technically it is wrong to resolve current. Yeah, it is correct. What you say is correct. That if you resolve current or you resolve the field, it is both. You get the same numerical answer, but one is physically wrong, one is physically correct. Okay. So, can you tell me what's the direction of the force? Today it's a Thursday. Other than Terence, anyone's name starting with a T? Trump. Like that also can. Like that also can. Okay. Somehow your name starts with a T. Somehow your name starts with a T. Yeah. In, out, left, right, up, down. Oh yeah, so let's take a look. So you got your field pointing this way, and then your current, okay, pointing this way might be a little bit too difficult, so you point the current reverse. Field this way, current this way, so it's out, but you need to reverse it, so it's in. Okay, so it's in. Alright, so this is the direction part of things. Remember, it's always the perpendicular component, and this is where the equation comes in. The magnitude of the force is equals to BIL sine theta. This is the equation. This is the magnetic field strength in Tesla. You must have heard of Tesla before. If you haven't heard of this person called Tesla, probably you haven't watched the movie called Prestige before. Have you watched this movie called Prestige? Oh. Sorry? The one, the magician one? Yeah, yeah. Oh man, that's such a wonderful movie. Oh, Hugh Jackman. Mine. It's a rivalry between magicians, man. It's amazing. He was featured there. And not the real person, obviously. In Ampere or Ampere? We had a discussion about this. Angle between the field. And for you, I'll say just current. Even though actually technically it's wrong to say that it's the angle between the vector and the scalar. Does it make sense, right? It should be a vector and vector. But if I tell you that it is the angle between the field and the current vector in the direction of the length of the wire, then forget it. It's too mouthful. Okay? So just take it as the angle between the field and the current. Okay? So let's try some problems on this using this equation. Let's try a very simple problem first. Let's see how many of you will fall. Okay, I shall not say too much. Let's see how many. Are you like really cold? Some of you are like going as the lesson. Current is 2 ampere. Field is 4 Tesla. Angle is, okay, if you just do it on your own, length equals to say 2 meters, and let's give it another number, 6 ampere, big current, and angle over there is 30 degrees. Find the force, meaning the direction and the magnitude. Do it on your own. Let other people have the chance to make mistake. If they are going to make mistake. If they are, then they will learn. I give simple numbers now, so I don't test you on your math. I test you on the application of the equation. Someone is doing something correct. So, simple numbers, no need to use calculator. Please don't use calculator. I'm sure that your teachers have taught you your timetable very well. I'm surprised that some of the IB students that I taught, sometimes they even have like 8 times 6. Okay, let's have a dipstick kind of a test. Ayo, no need to do until so rigorous one. Relax. Should be able to use this. Sin 30, what's the answer? Half, correct. So sin 30 half. So the answer should be 4 times 6 times 2 times half, right? So the answer should be 24. 24 here. BIL sin 30. Correct. Correct, Lauren? BIL sin 30. It's just sin 30. Yeah, simple question now, but there is a very subtle trick there. This 30 degrees is nonsense. In this context, yeah, it's nonsense. Let me show you why is it nonsensical. It doesn't help at all. Okay, this is okay. Let's take this as a current. Let's take this as a field. The length of it as the field. So the field is pointing inwards, right? And the current is this way, right? Agree or not? The field is pointing in, and the current is pointing here. What's the angle between the field and the current? 90. 90. The 30 there is just yeah. You know why? People will say after exams, you know what will happen? The students will come to me and say, oh, lost, careless mistake. Yeah, careless mistake. But actually, it's not careless mistake. It's because you're not careful enough with the definition of the terms that you're using. Yeah, careless mistake is like, oh, everything careless. Yeah. Probably I'm a careless mistake. Don't brush things off. Careless mistake. No, nothing is careless. Usually it's the lack of care for something. That's why you something important, like the definition of this. Yeah? Okay. Yes, Shani? Anyone got the? Oh, okay. No. If you don't catch it, don't try to catch it. Certain jokes is better not to catch it. Okay, so simple BIR. Ready? Up one notch, ready? Up one notch, ready? Actually, it's up two notches. Okay, let's take a look. Okay, try to visualize this. So I got a current over here, I got a wire. How does the wire look like? The wire looks like this. Okay? The wire looks like this. Then it rests on a ram. And this is 30 degrees. The field is this way. The mass of the rod is 50 grams. The length of the rod is, say, 1.5 meters. The field strength is 400 millitesla. And what else do you need? That's it, actually. So I would like you to find the current, both the direction and the magnitude, so that the wire will stay on the smoothed ram. So when I say smooth ram, what's the coefficient of friction? 0, correct. No friction. I'm trying to make your life easier lah. Because if I were to include friction, can you see that there will be a range of current that the wire will stay on the ram? If it is too small, it will slip down or up. If it is too... Oh, you put something on the ram, it just goes up. Come on, which planet are you on? It slips down. Then if I have a very big current, it is possible for the wire to go up. So I'm making your life a little bit simpler by saying no friction, so there's only one current where it stays still. I'll give you 1 minute to just try to understand what on earth is happening here. It's very important figuring out what is happening. What are the forces acting? How is it able to stay on the ram? Before you even construct equations, okay? Before you even construct equations, this is important. Understanding the scenario. By the way, can you see that there are only 2 ways the current can flow? Again, students can surprise you with the most creative answer. The current over here is towards the left. It's like, what? It's like, give it to you, you return it back to me. It's like, guess 50%. Come on. Even if you make a guess, it's 50%. Okay? Please think carefully. It's either in or out. Then think, if the current goes in, what's the direction of the force? If the current comes out, what's the direction of the force? Then you know that one of them is impossible. Then you know that it has to be one of the directions. So is it going to be coming out or is it going in, the current? Has to be out, Has to be out. Now, if it comes out, then the force will be this way, right? Yes, correct. Yeah, FB. Then what do you do? Then FB equals to mg. FB equals to mg. Easy, right? FB equals to mg. Just somehow just anyhow whack. Hey, I'm giving you examples from real life examples and real life mistakes the students will make. Just FB equals to mg. Heck about the direction, YOLO. YOLO, just FB equals to mg. Heck. No, you know that these are not in the same direction. So vector, you must think direction. Vector, think direction. If the wire were to move, obviously it cannot move into the ram, right? Come on, what sort of wire is that? Adamantium wire or what? So this cannot move into or move into. If it were to move, it has to move here, what, right? Agree? So we need to resolve the force. Okay? Now the weight, which is the mg over here, can you tell me what is the component along here? Mg, sine, cosine, or tangent? If you choose tangent, you're off tangent. So which one? Sine, sine, correct. Mg sine theta. This is the component of the weight. Make a second. So this one, BIL, sine what? Sine, sine. Sine, sine. Sine, so sine. So it's BIL over cosine. How? Okay, let's think carefully. Let's think carefully. If you got a force, remember when you resolve a force, it has to be the hypotenuse. That's the rule. It has to be the hypotenuse because you cannot break things down into bigger parts. You cannot break things down into bigger parts, so it has to be smaller. So this has to be the hypotenuse. This is theta, this is theta, so therefore this is FB cos theta. Easy already, no? So this one is just BIL sine theta cos theta. You sub 30 into these two, then you equate it to mg sine theta, then correct already? Correct no? Correct. BIL, so mg, so let's write this down. Mg sine theta, which is this is 30 degrees. So equals to BIL sine theta cos theta. These are both all 30 degrees. In fact, life is even better for you. Just strike off the sine theta. Why? Why? Where does the one come about? My acting skill not bad. So why? What's wrong with this 90 degrees? What's wrong with this 30 degrees over here? Because the angle theta, remember I kept reminding you, you must say it out in your mind. Say it out and then remind yourself. You must say it out. Not impressionistic kind of. Theta is the angle between the field and the current. So look carefully. The current is this way and the field is vertically downwards. The angle is 90. Correct. Careful. This is not the angle between the field and the current. It's nothing to do with the current and the field. It's just resolving it. So you have to have that clarity of mind. Okay? Practice that clarity. Be very careful. Okay? Then solve lah, people. Just solve for it. Finish it through. Get the value of the current. If you do it correctly, you should end up with a tangent theta somewhere. I think it's mg tangent theta and then times divided by BIL. Why are there people walking around already? I thought we still have like 20 minutes more. Or 40 minutes more. 40 minutes more, right? Yeah. Why are people walking around already? I gave you quite nice numbers or what? Let's try to do it without calculator. Come on, calculator damages your brain. Seriously, it's just like you're okay to walk, then you use a walking stick, and then very soon you depend on a walking stick. So let's take a look. 50 gram is 0.05 G times that's mg times tangent 30, and that's divided by B, which is 0.4 times 1.5. And that's it, right? mg tangent theta divided by BL, which is equals to I. B is 400 millitesla, which is 0.4. It's 0.4 Tesla, okay? So it's 0.05 times 9.81. Tangent 30 is sine 30, so it's 1 upon root 3 divided by 6. So it's equals to 0.05 times 9.81 divided by 6 root 3. This is about 1.7, therefore this is about 10. So it should be about 0.04, 5, 6, about that order. So what's the current eventually? 0.0? 0.47, that order of magnitude you sure no? 0.48. This is about 10. This and this should cancel off the order. Is it? Oh yes, mistake here. Yes. Thank you. Thank you. So therefore it should be 0.4 something. Yeah. So it's 0.4 what? 47. Okay. Thank you. That's victory cry or what? Okay, this is a little bit boring, but you have to know, no choice. So this is actually the way we define magnetic field. Now let's take a look. Remember your topic 6 or not? Topic 6. Topic 5.1. Wow, that's it. Goes in. Topic 5.4. This one don't chew, this one is now. Topic 6, you remember what is it? No? Circular motion and gravitation. Remember gravitational field. So we define gravitational field strength by this symbol called G, which is defined as the gravitational force per unit mass. Right? The definition of electric field is force per unit charge. Okay? Make a guess. What's the form? Think for 5 seconds. What's the form? Yeah. This is the defining equation. So we can see the form all fields related to force. So it's force per unit mass for gravitational field, force per unit positive point charge for electric field, force per unit current per unit length, and perpendicular to the current. The detailed definition is inside your notes, but I wanted to string things up together so they can see how force is being defined. How field is being defined. There's always a force per unit, the quantity that the force is acting on. Okay? That form is consistent throughout all fields. Okay, so this is the definition. The detailed definition is inside your notes. Go and look for it. Cool. Now, next thing I'm going to go into, and then it will lead on very nicely to the next thing, which is force on a moving charge. This one is force on a current. Now we go on to force on a moving charge. How many of you have seen the Northern Lights before? Anyone? Don't be shy, it's okay. Haven't? No? Okay. Not the wallpaper kind, it's the real. A lot of wallpaper got Northern Lights, I realize, but the real Northern Lights. Okay. It's rather elusive, the Northern Lights sometimes. You wait for the whole night, it doesn't come out. You travel on the road, suddenly it appears. Okay, the reason why I asked this is because it has something relevant to what we're going to do very soon, which is force on a magnetic charge, or on a charge, moving charge, in a magnetic field. So let's take a look, yeah? You got the, say, charged particle, say a current, going this way. Now, a current comprises of moving charges, right? So let's assume that it's positive charges that move. Like it is completely wrong, but let's assume it's a stream. Let's assume there's a stream of not moving atoms. It's a stream of moving positive ions. Positive ions. So you got the magnetic field acting this way. So force equals to BIL. Let's take away the sine theta because they're perpendicular, because sine 90 is 1. So B, current is defined as the total charge moving a point per unit time. So it is the number of charged particle times the charge of each of the charged particle divided by time. So that's current. Now let's take a look. So B, Q, L upon T. What's the distance traveled per unit time? What is it equals to? Exactly. So it is equals to NBQV. Now therefore, if I take the force divided by n number of particles, this is the equation for the force per unit charge on a single charge particle, because it's F divided by n, which is the number of charged particles. Okay? So this is the equation. The more complete form, of course, which is something that we ignored, this angle is the angle between the field and the current. But now we don't have current. Now we only have moving charge. So it's the angle between the field and the what? What's the other vector in this equation? Come on, relax. After scamming so many times, I must careful. Careful. So which are the two vectors? This one and correct, velocity. Charge not then sir, why charge got plus and minus? Plus and minus simply means two kinds of charge, not because of direction. B and V. Remember this mantra. You must, whenever you remember equations, you must remember what that comes with it. What does it mean? Okay? What does it mean? Now this is simple, F equals to BQV sine theta. We're going to take a look at some of the uses. In chemistry, do you learn this thing called mass spectrometer? You do learn that? Okay, we'll come to that very soon. So let's take a look. You've got a positively charged particle and it travels inside a region where the field is pointing out of the page. Can you tell me what's the direction of the magnetic force of the particle at this point? Coming out of the page? You sure not? Use your left hand rule. Well, some people can imagine one. We don't even use it, I can imagine. Wow, really a kowtow. The spatial intelligence really high. How? Anyone? Up, down, left, right, in, out. Down, right, it's down. Yeah, so it points out. Okay, difficult for you to. So relax now. Remember, reverse the direction of the field. Yeah, so reverse the direction of the force is down. Okay, reverse one of them, then reverse back. So the force is down, and therefore the particle goes this way. Agree or not? After a period of time, it will go down. Huh? Some of you still having difficulty with the. See, pointing out this way, current towards the right. Current is in the conventional current, by the way, conventional current, where the direction of positive charges move. So do you agree that you've come down? So the force is downwards. Change already, If you use the Fleming's left-hand rule, the force is always perpendicular to the current. It's always perpendicular to the current. Then it goes this way. 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 Can see now? One motion. Circular, correct. Yep. So very often we put BQV equals to mv squared upon r equals to mr omega squared. Very often. Yeah. In fact, this is the technique, even up till now, this is the technique to what they call confined charged particles, confined fast-moving particles. If you have the chance to go CERN, rub it in now, rub it in. Rub it in. If you have this is you're learning CERN physics now, I mean seriously. It's okay. Your mind is there. You can always go Google CERN.ch. You are there immediately. Yeah, your body is here, but your mind is there. So you go in circular motion. This is how you trap fast-moving particles. Yeah, and the problem is, can you see that because let me. The radius equals to, if you look at this part, you cancel, you'll find that it's equal to mv over bq. And because this is not relativistic, let's take simplistic view of the thing. So because as v increases, your r will increase, and that's why the circumference of the CERN has to be this big. The circumference is 27 kilometers. It's huge. With 10% in Switzerland, 90% of it in France. Why? Hadron Collider. So why? Why 10% in Switzerland, 90% in France? The 10% includes the HQ, which is the CERN place, if you get to go there. Why? Because Switzerland, one yogurt X dollars in France is X upon 3 or X upon $4. So that's why 90% of the collider is in France. Only the HQ is in Switzerland because it's supposed to be international collaboration. So Switzerland is a neutral country. Politically, it's more correct. Yeah? So that's why when V increases, R has to increase. Now they're planning to build a super collider, super large collider, where the circumference is about 100 kilometers. Yeah? So it's a lot more. Yeah. 4 times the tunnel. 4 times the tunnel length. So this is the equation for R. What I want you to deduce is the equation for the period. Can you deduce the equation for the period in terms of something? I want it in terms of B, Q, and M. Give it a try. Try to come up with the expression for the period only in terms of M, B, and Q. You'll find something interesting, the period. Imagine someone running around a track, someone who runs very fast around the track versus someone who runs very slow around the track. Who do you expect to finish the track for the run faster? Or I tell you that someone runs very fast, runs on the track, and then someone slow runs on the track. Who finishes the run faster? Obviously the person who runs faster, right? You'll find that this is equals to 2 pi m upon bq. This is 2 pi times m upon bq. So what is interesting about this formula? Anyone? Okay, let's check whether you're able to derive this first. The fastest way to derive this is this. BQV equals to mr omega square. So BQV upon r is equals to m omega square. This is actually omega. If you recognize this, V equals to r omega. So omega is equals to V upon r. So you can cancel this out. So omega, which is equals to 2 pi upon t, is equals to BQ upon m. And therefore, you rearrange the equation, you're going to get period. That's the fastest way, I think. Okay? What is interesting about this equation for period is that it is independent of radius and also independent of velocity, correct? No matter how fast you move, even at relativistic speed, it is still the same time to go through one circle, which is very interesting to think about it, okay? And one of the collider that makes use of this property that it doesn't depend on the speed is this thing called the synchrotron. Synchrotron. It's a very early particle accelerator, which, if you go to CERN, you also get to see. Oh yeah, you get to see the original, the first collider. Decommissioned, but it's still there. It's there. Yep. In fact, it's it's still it's still at the original location. It's still at the original location, that machine. It's quite amazing. Okay, go and check it out, synchrotron. And then there's this thing about synchrotron radiation, and you can read up more about this. Very interesting. Okay? Relax. Finish already. Finish. Okay, now let's take a look at the basic construct of a mass spectrometer. Okay? Then you realize why you need something else. That's not the end of the story. There's something else that you need. So say, for example, you do CSI and then you got a small sample, you vaporize it, you atomize it, then you send it through this mass spectrometer. You ionize it, meaning that it has, okay, so say, for example, you got a field that goes into the page, and then you got negative charges. Okay, why negative? Let's say there is negative charges. So the atoms becomes negative charges, and then it goes into this magnetic field. So it goes this way, the current points opposite direction to the motion, so it experiences a force this way, pulls it into different orbits. Why? Because remember, R equals to mv divided by bq. Different m will have different R, since they are in the same magnetic field. Charge-wise is not that difficult to manage, because if you have singly charged and doubly charged, the radius are distinctly different. You divide by 2, so it's separated quite far. Or divided by 3 is separated quite far. So, do you see that there's something else that you need to control? Exactly. If you don't control the velocity, the different radius could be due to the different speed. So you need to do some magic to the particles over here before you allow them to pass into the magnetic field, so that any differences in the radius position is solely due to mass. So how do you do this? Sorry? What timer? Go through, don't go through, go through. No, you can't. So this is where the experimental physicists are really, really smart. So what they do is they set up this thing called a velocity selector. Let's take a look. Positive, negative plate. Can you see that this electron or this negatively charged particle will experience a force towards the left or right? Left lah, positive attract lah, right? Oh, heng ah. Luckily. Okay, otherwise I'm going to reteach 5.1 already. Can you see that if I were to apply a magnetic field such that the magnetic force is towards here, it is possible that these two can cancel and this particle can go right through. So what's the direction of magnetic field that I need to apply? In, out, left, right, up, down? Down? How to down? The field down, then the current also down there. Bang. Yeah, the force is this way. Yeah, the current is this way, so it's in. Okay? It's in. Right. Now, can you see that? Force B equals to BQV. Force E equals to QE. You equate these two, you pass right through. Boom, boom. Can you see that by putting a very tiny slit over here, and by controlling the values of E and B, I can control the speed of the particle that passes through. Take a look. If a particle with speed bigger than E upon B, would it deflect left or will it deflect right? Which force depends on speed? Which force depends on speed? Magnetic or electric? Magnetic, correct. So if the speed is higher than E upon B, then it will go this way. Yeah. If the speed is lower than E upon B, it will go this way. If the speed is equal to A upon B, it will go right through. So if I want to choose a certain speed, I just need to make sure that this ratio, which I can vary, and then only the particle with that speed will go right through. So this is called a velocity selector. So therefore, I've successfully controlled this one. Therefore, the only thing that affects the radius is the mass. Yes? Sorry, again? Losing a lot of? That's true lah. Some of the samples will actually have a range of speed. I guess what you can do is, remember at different temperatures, you've got a Maxwell's distribution. So at different, this is probability, this is probability. This is speed. And at different temperatures, you actually shift T1, T2, you shift the probability left and right. The higher the temperature, the more it shifts towards the right. So I think what you can do is by changing the temperature of the ions over here, you can try to make sure that most of them are in that range that you're looking at. So that's what you can do. Can? You will still lose lah, but at least you lose lesser. Can? Cool, huh? Mass spectrometer, basically it's back to this simple physics. CERN, also simple physics. Ding ding ding, sun coming. Ding ding ding, coming. Yeah. Okay, Ken. Okay, let's throw a spanner in now. What? No worries, Yiding. No worries. Let's throw a spanner in. Okay. Okay. I got a negatively charged particle at rest at that point. I got a magnetic field into the page. I got a positive plate on top, negative plate below. How will the particle move subsequently? Up, down. How will it move? Simple lah. It will move and then stuck here lor. Right? It will move and then stuck there lah. Ding! I'll give you 30 seconds. Think about what, if as it moves, obviously it will move upwards, right? Initially it will move upwards. Then what will happen to it? Okay, let's assuming that the magnetic field is very strong. Let's assume the magnetic field is very strong. The magnetic field effect is very strong, so that the magnetic force has significant effect on the particle's path. It will go circular with constant radius. So the speed is always constant. Huh? Huh? So obviously it's not going to ting stop there, right? It's not so simple. So how will it move? It will go up. Okay, remember the radius obviously is going to go into circular motion. The radius is proportional to the speed. So the further it goes up, the faster it moves. The faster it moves, the bigger the radius. So what it will do is as it moves up, it will curve. And how? Oh. Then what happens? Continue happily ever after, or then it will come down. Then as it comes down, does it speed up or slow down? Does it speed up or slow down? Then what happens to the radius? Yeah, so it will. Woo woo! Yes, correct. This is what happens. Okay? What? What is this abomination? Yep. So this is how this is in your syllabus. This is in syllabus. This is not in syllabus. Okay? Let me be very clear. Yeah, not in syllabus on that side one. This side is syllabus. Okay? Yes. Ah, right. So you're saying that the electric charge itself moving, does it have magnetic effect by its own? Now, usually we ignore that. Yeah, the magnetic field is an external field, not the field due to the electron. Yeah, negligible. That means the magnetic field due to the current, due to the moving charge, we ignore that effect. Okay? Well, it's a good point surfaced by you. Okay. Ready for the next one? Okay, questions that I like. This is, of course, difficult because of the complexity. Questions that I like is like this. Is the positively charged particle moving clockwise or anti-clockwise? Huh? Both sides can what? Cannot. Only one direction. Clockwise or anti-clockwise? Now let's make your life a little bit more difficult. Negatively charged. Is the particle moving clockwise or anti-clockwise? Sure not. Sure not. this becomes equivalent to actually it's correct. You're correct. Okay, what's the direction of force at that point? It's moving in a circle, so the force must be towards the center. Okay? So once you establish that, this way, the current is this way. So you should go anti-clockwise. This is lame, right? Hey, some students stop there. Then say that it's anti-clockwise. So it is going clockwise because it's negatively charged. Can? Be careful. So I like this kind of question because there's no numbers, but yet there's quite some thinking. Okay? Let me show you another very interesting effect, which is which you can possibly use. Okay. A and B. We talk about positive, negative charges attracting. We talk about mass attracting. A and B, light currents, do they attract or do they repel? You sure not? Positive, repel. Up should repel. Okay, so let's see. What's the direction of field due to A on B? It's inner. But be very careful, this field over here is not due to B itself, it's due to A. Then you use a left-hand rule, it will be this way. Therefore, if you use the same reasoning again, it will be this way. So light currents attract. Light currents attract. Now I'd like to bring you back to the first, very early question that we went through just now. Remember this one? Loop A, loop B? What sort of relation does it have? Now remember that we decide that when the current goes this way and is increasing, the field points in, so to create a current that opposes the change in flux, it must go in and therefore it should go out, so it should go this way. For A. Okay? Now take a look at this section. Okay, is it in or not? Let me just confirm. Oh, sorry. This way out, so it creates in the other way. It should be this way, this way. Okay? Now, can you take a look at this portion? If like currents attract, what do you think unlike currents do? Yes, correct. Can you see that the force experienced by this will be this way? Can you see that the force as a result of the induced current is trying to reduce the area? Why so? Remember Lenz's law. Any current that flows is always in a way to oppose the change. Take a look. When you got a current going this way, it is actually producing a flux that is increasing in this direction. Now flux depends on what? Field strength and area. So while the field strength is increasing due to the increasing current, you want to reduce the area so that the flux is decreased. Can you see, no? Can you see what the current is actually trying to do? It is trying to flow in a direction to decrease its area, which achieves the same result as reducing the flux. Are you all okay? Remember that Lenz's law states that the induced current will always be in the direction to oppose the change that causes it. The change over here is an increase in flux. In this case, it is out of the page. Flux is dependent on two quantities. Magnetic flux is dependent on two quantities, the field strength and the area. Yeah? So because it is an increase, what you need to do is to try to push this down or push this down. Just now, the reasoning that we used was, since the field created by this is out and increasing, you try to create a field in by having a current this way. That was one route of explanation, which is this one. The other way of understanding is that you can actually reduce the area. So to reduce the area, you need to push this in. To push this in, the current must be opposite direction to the external current. That's the other way of reasoning. And it arrives at the same conclusion, the current will be going clockwise. Okay? Are you alright now? Can follow? What I'm trying to show you is that by going through different routes of reasoning, you must arrive at the same conclusion. Why? Okay, Now, if you were to try to create a robot where the magnetic, by applying this one, okay, if I pass a very large current over here, what will happen to the spring? Oh, that's a little bit extreme. That's a little bit extreme. Yeah, a little bit. I'll show you, actually, it kind of does. I'll show you why later. Long time ago. Long time ago, my university has it. This is the new, like, what? Love yourself campaign kind of thing. Love yourself campaign. Okay, so if you pass a very huge current, can you see that this section and this section, the currents are in the same direction? So, like currents. So what happens to the spring? It will, yes, correct. So you pass a current, you release the current, comes back. Yeah. So by passing big current, you can cause it to contract. But you find that to have a considerable force, your wire will vaporize. Explode. But what he said is actually true. Like in my college in the past, which is one of the best college in the world, Imperial College, advertisement. So if you pass a very big current over here, can you see that this big current can be broken down into small little currents? So if this current is in the order of mega amps, can you see that these small little wires will attract each other? So they will basically compress. So the college I was in, they were trying to achieve fusion by passing a huge current through a wire, causing it to compress and achieve fusion. Yeah, and unfortunately, I think it's unsuccessful. At least we learned that it is not successful. Yeah. So it's by tapping on the compressive force of the huge current passed through a very fine wire. They were trying to achieve fusion. Relax. You're trying to say that you compress so much that it passed. Quantum tunnel through. Possible. Why not? No. Once it touches, if it is an insulated wire, it will touch and hold there. If it is bare metal, then it will just pass, becomes a true current. I think so. I think they'll uncoil. Yeah. Possible. I never thought of that, but I think most of the situation I thought of is that the wire itself is insulated. Yeah. But if he says that if it is bare metal wire, if it touches, then what happens? I think you'll lose that. Yeah, it's short circuit, but it's already short circuit. in a way. Okay? Unfortunately, I don't have time to go through the relativity. I will go through it with you online tomorrow. I will record a video and then I'll post it. How you go through using Lamb contraction, I can show you that magnetic effect doesn't exist. Kappa kappa doo. Yeah. It's like when you learn that G is 10, G is 10, G is 10, G is 9.81. Then someone say G is not 9.81. At the equator is 9.79. You know why not? You can think about this or why? You can think about why G is 9.